kind of skip a step here, and I'm going to go straight to our matrix of A minus lambda I. So I'm going to have -1 minus lambda, -1 because of the coefficient on that negative y, 1 and 1 minus lambda. I think I pulled these from one that we should have some complex eigenvalues. They may not all be complex on the sheet, but I'm hoping at least a few of them are. So -1 minus lambda times 1 minus lambda, and then minus -1 times 1. So if I'm careful about distributing this out, I've got -1 times 1. -1 times negative lambda is going to give me a positive lambda. Negative lambda times positive 1 will give me a negative lambda, and then a positive lambda squared and plus 1. Oh, that's fun. Told you I pulled these from an old worksheet. So lambda squared is equal to 0. That's cool. So lambda is equal to 0. But yeah, so I'm just going to keep going with a lambda of 0 because it's interesting. This is what I get for pulling an old worksheet. So if lambda is equal to 0, then to find those eigenvectors, normally we have 2 eigenvalues that is going to lead to giving us 2 eigenvectors. So if I plug in 0, I have -1, -1, 1, 1 times xy would give me 0, 0. So if I look at the top equation, that's saying -x minus y is equal to 0. Bottom equation is just saying x plus y is equal to 0. Both of these are telling me that y is equal to -x. So I can choose an eigenvector like 1, -1. And if I went to write my solutions, normally our solutions look like C1 e to the lambda 1. Am I still on the screen? No, not quite. C1 e to the lambda 1t times B1 plus C2 e to the lambda 2t B2. But here I've only got one eigenvalue and one eigenvector. And with that eigenvalue of 0, it's a really exceptionally boring equation. This really just tells me that x is equal to some constant and y is equal to the negative of that same constant. Okay, super boring. Didn't mean to give us quite such a boring starting one. So should we look at the second one instead? Minus, oops, 2 minus lambda times 1 minus lambda plus 8. So I am looking at lambda squared, make sure I get this part right, minus 3 lambda, plus 2 plus 8. So lambda squared, sorry, I was going to jump straight to, yeah, I'm just going to jump straight to. So that means that my lambda is going to be equal to 3 plus or minus the square root of 9 minus 4 times 1 times 10.
You can factor this, don't you?
Oh, does it factor?
I mean, I think so.
I think it's not going to if I would get a negative inside the square root. So if
It was like positive. Or you can do that. -5 plus 2 5.
so if I were to do lambda minus 5 times lambda plus 2, I won't get a positive 10. So this doesn't factor. So I had to use quadratic formula. So thinking about this cleaning up a little bit, I'm looking at 3/2 plus or minus, and now inside my square root looks like I've got -31. So that's gonna be the square root of 31 over 2 times I. And just as a reminder that I is equal to the square root of -1. Up until this point, we generally ignored these complex solutions, but the complex solutions are telling us interesting things now that we're talking about it in the system of differential equations. So the short version of this is having a complex solution means that I know that there's some kind of spiraling behavior. And the fact that my real part is a positive number tells me that it's an unstable spiral. So there are two pieces to this. In terms of seeing that spiral behavior, we can do that by graphing some vectors in a direction field to kind of see what that spiral behavior looks like. To get at the stability piece of this, we really need Euler's formula. And what Euler's formula says is that if I have e to the a plus b I t, right? Because that's what was going to happen if I stuck that eigenvalue into our formula. This can be rewritten as e to the a times a combination of sines and cosines. Now, why are we not talking about that in 19C? Because we didn't do trig in 19C. So I'm just hiding the, it's in the textbook because we've shifted into the book for 17C. We're not going to talk about it in this class. We're not going to have to unpack this because we didn't do sines and cosines. But I just want to show you sort of what's happening behind the scenes for why our stability matters, or like where the stability comment is coming from. So all we really need to know is that this sine and cosine behavior is making something oscillate. This part right here is essentially giving me the amplitude of the oscillation. So if that A value up there, if this thing, I need a T up there, but if that A value up there is positive, then my amplitude of the oscillations is growing as T approaches infinity, because e to the positive infinity is getting large. The amplitude of my oscillations is going to go to 0 if that A value is negative. So for the context of 19C, we really just need to know when I've got a complex value that tells me that I've got a spiral, and then I look to the real part to decide. In this case, it's greater than 0, so we're going to be unstable. And that's the extent of what we're going to be expected just in terms of this class. Now, I did one of these. I think I just did one on Tuesday where we graphed the null lines and picked vectors along the null lines. That's going to be something that for sure, if it doesn't come up in lecture tomorrow, it'll come up in lecture next week. So I'm going to go ahead and sketch the null lines so we can show that spirally behavior. So sketching the null lines means I'm setting each of my derivatives equal to 0 and sketching those graphs. So if 2x minus y is equal to 0, then I know I'm looking at y equals 2x. And if 8x plus y is equal to 0, then y is negative 8x. So I'm going to go ahead and sketch those null lines. And so I'm going to have y equals 2x. And I should use different colors, but that's the y equals 2x. So that is my dx dt equals 0 null line. Y equals negative 8x. It's going to do something like this. And that is my dy dt equals 0 null line. And to get a sense of the behavior around this equilibrium 0, 0, I can choose vectors on the null line and sketch what those direction vectors are going to look like. Now, why am I doing it this way and not sketching the eigenvectors? Well, because for complex eigenvalues, the eigenvectors are complex. So trying to sketch those becomes more complicated. So when I have complex eigenvalues, sketching along the null lines turns out to be an easier option. So everywhere on the dx dt null line, I'm not changing in the x direction. So these vectors have to point directly up or directly down. So everywhere along this null line, I will be up and down. And everywhere along my dy dt null line, if y is not changing, then these vectors have to point left or right. And if we pick points on the null line, we can figure out what direction those arrows should point. So I'm going to pick something on the line y equals 2x. So I'm going to pick a point over here, like 4, 2. Nope, other way around. 2, 4. If x is 2, y is 4. And if I'm standing at the point 2, 4, I just want to know when I plug in 2 and 4 to my dy dt equation, is it positive or negative? Looks like I'm going to be positive. So I know that these arrows over here are pointing up. If I choose a point along my other null line, so let me choose a point over here, like -1, 8. And now I want to know, are those pointing left or right? So I'm going to plug those into my dx dt equation. So if x is -1 and y is +8, then it's negative, and I know I need to be pointed to the left. So everywhere over here, my arrows are going to point to the left. I can keep plugging points in, or I can use the fact that I know that the only way to switch from positive to negative is from passing through 0. So if I'm up here and I cross the dx dt null line, I know that my arrows are going to flip. And if I'm over here and I cross the dy dt null line, I know that my arrows are going to flip. But we can also plug in points to show that that's true. So I can keep choosing points that are on my null lines. So I could pick a point over here, like -1, -2. That should solve this equation. And if I plug in -1, -2, I'm going to get that dy dt is negative, which confirms that my arrow should point down. And now you can kind of see that we've got this spirally behavior. Since I know that it's going to be an unstable spiral, if I were actually sketching a trajectory here, I would need to show that my trajectory is spiraling out, that the amplitude is getting bigger. So if I started over here and I was trying to show a trajectory, the important things are I need to cross the null lines in the direction, like in the flattened out directions. So I'm going to cross this null line and then I'm going to get it pushed over here. I'm going to pass through that vertically. Again, my amplitude is getting bigger. I'm going to cross through this one horizontally. My amplitude is going to keep getting bigger. I'm going to cross through this one vertically. And that spiral is going to kind of keep going. By the way, just to continue on the graphing bit of this for a second. So let's say that this point up here was 1, 4. if I needed to sketch what was happening for X and Y over time, based on that, my X started at 1, my Y started at 4. And both of these are gonna have some kind of oscillation behavior. So if I think about this, I didn't really give myself enough space here. So manual zoom out. So my X value starts at 1. And if I think about like just moving along this trajectory, my X values shrink to 0 and then they get negative. So they get negative out to here. And then they're still negative, but they come back to 0. And then my X values are getting bigger as they move out this way. So in terms of what's happening on the graph, I'm going to just label some points here. So I'm going to label this point A. I'm going to label kind of the top of my graph up here B. I'm going to label the side over here C, the bottom down here D, and the side over here as E. Just to give a sense of like what's happening at X and Y for each of those points. So A is starting out at 1. By the time I get to B, it's a little bit negative, but the most negative it goes is C. So I'm going to get down here negative, and the most negative it goes is at that time C. And then I'm growing again, and the most positive I'm going to get is E. And that's like further to the right. It's a bigger amplitude than my pole to the left over here at C. So I got to show that it got somehow bigger up there. And then my X values start shrinking again. So that's kind of like I'm at point E. For the Y direction, we started at 4 and it actually goes up first. So I get a little bit bigger than 4 for a minute, and that little bit bigger than 4 is happening at point B. And then it shrinks down to 0. And then gets more negative all the way down to some value D. And then gets positive again, and this keeps going. So I've got some sort of oscillation behavior. So there's no real component this time in terms of the eigenvalues, meaning if I wrote this, it could be written as 0 plus or minus the square root of 3i. When that real component is 0, we call this a neutral spiral or a center. Now, what's going to happen when we have a neutral spiral or a center? It means that we're still going to have that oscillatory behavior because of that I component, but we're not going to have a change in amplitude. The other way we can frame this is, I know that they won't necessarily be a circle because they might be kind of more ellipsish, but I'm going to return to the same place I start. Stable? Stable? Yeah. Doing the same thing. You got a positive one, you got a negative one. Sounds like we should do some algebra together. Okay. Okay. So I'm looking at the determinant of -1 minus lambda, 3, -1, and 2 minus lambda. So -1 minus lambda times 2 minus lambda, minus a minus, so I'll just write that as +3. So if I distribute that out, I think I'm gonna get lambda squared. That'll be a plus lambda, that'll be a +2 lambda. So +3 lambda minus 2 +3. So lambda squared +3 lambda +1. Does that look like what you've got? No?
It's negative.
Yeah, I'm gonna go one, two.
Oh,
Because it's -2 lambda plus then.
it's cool. Negative lambda. I already had a lambda. It's just how life's going today. Okay. So now if I write my lambdas, I'm gonna have 1, because it's negative b, plus or minus the square root of -1 squared minus 4 times a times c, all over 2 times a. Yeah. So I've got a negative inside the square root, so I know it's a spiral. And I know that the real part is a +1/2, so this is another unstable spiral. Woohoo! Good times. So as a quick recap, for a linear system of differential equations, we're going to find the eigenvalues. I'm just going to call those lambda1 and lambda2. And if they're both positive, what do I know? If they're both negative, I've got one of each. And if they're complex, meaning they're of the form A plus or minus BI, then I know they're spirals. And if A is less than 0, we're stable. If A is greater than 0, we're unstable. And if A is equal to 0, then it is a neutral spiral.
And this is the equilibrium 0, is taking from state.
Correct. So all of these, if it's a linear system, all of these are referring to the equilibrium of 0, 0.
Was that because we set them 0?
And because it's a linear system, 0, 0 is going to be my only solution. First of all, just from looking at this, how do I know it's nonlinear? Sure. Also, the x times y term makes it nonlinear. So there are two things that are making this nonlinear. If it's nonlinear, 0, 0 might be an equilibrium. It might not be. But the first thing that I need to do is to find all equilibria. Now, this is going to look a lot like when we were finding critical points back in chapter 15. So I'm going to set each equation equal to 0 and possibly get multiple equilibria out of that. I'm going to let you practice your algebra skills and see how many equilibria you find. Should we do the algebra part together? Okay. So on that first one, I can factor out a 2y. And then I think I'm left with 2 minus x. And on the second one, if I factor out an x, then I'm left with x plus y. So visually, the way I think about this is I've got these 4 pieces and I need to think about all the ways to match them up. So I can take that 2y, match it with the x, or I can take the 2y and match it with this. I can take the 2 minus x, match it with that, or match it with this. So what does that look like in practice? Well, if 2y is equal to 0, that means y is equal to 0. And if 2 minus x is 0, then x is 2. This would tell me x is equal to 0, and this would tell me y is equal to negative x. So if I think about all of those possible pairings, if I start with the y equals 0 and I match it with x equals 0, that gives me the point 0, 0. If I match up y equals 0 with y equals negative x, that also gives me the point 0, 0. So now I'll move on to the x equals 2. Can x be equal to 2 and 0 at the same time? No, it cannot. X cannot be both 2 and 0. So that does not lead to an equilibrium. But x equals 2 down here leads to the point 2 comma negative 2. So these are my 2 equilibria. We good with that? So now comes the fun part. So this isn't linear, but we would like to linearize it, meaning we would like to take these equations and very near that equilibrium, treat them as if they are linear equations. So I'm going to give us the context that's in our textbook, which is to go ahead. This matrix is called the Jacobian matrix or the Jacobi matrix. And my Jacobian, I'm going to get from thinking about, I'm going to relabel this top equation as F, and I'm going to relabel the second equation as G. And I'm going to use the partial derivatives to say very near this point, if I want to treat it like it's a constant, I'm going to look at the partial derivative near that point. So I'm going to construct this matrix, and I'm going to label the outsides of the matrix first. And I'm going to construct my matrix by, in the top row, taking the partial derivatives with respect to the f function, and in the bottom row, taking the partial derivatives with respect to the g function. So in my top row, partial of my f function with respect to x is going to be what?
2.
And in my top row, if I take the partial with respect to y, I'm going to have 4 minus 2x. If I do the same thing in my bottom row, partial with respect to x and partial with respect to y.
X.
So this Jacobi matrix is giving me sort of generically what that linearization is going to look like near my equilibrium. So at 0, 0, this matrix becomes 0, 4, 0, 0. And then at our other point, 2, negative 2, our matrix becomes 4 0 2 2. So I can read off my eigenvalues from this one. My eigenvalues are gonna be 4 and 2. So near the point 2, -2, this is going to behave like an unstable node.